Solar panels are an innovative and essential technology that converts sunlight into electricity, playing a pivotal role in the global shift toward renewable energy. These panels are meticulously engineered, comprising various materials that work in harmony to maximize efficiency and durability. This article delves into the key components of solar panels and explains the intricate manufacturing processes behind them. Key components of solar panels are composed of several layers, each with a unique role in energy conversion and system protection. Below are the primary materials and their functions. Silicon solar cells. The core of any solar panel is the silicon solar cell, a semiconductor material that converts sunlight into electricity. Silicon comes in three primary forms: monocrystalline silicon, manufactured from a single crystal. This type is highly efficient and long-lasting. Polycrystalline silicon, made from melted silicon fragments. It is less efficient, but more cost-effective. Amorphous silicon, used in thin-film solar panels. It is flexible but less efficient than crystalline types. Encapsulation layer. Solar cells are encapsulated using materials like ethylene vinyl acetate (EVA). This layer protects the cells from moisture, dust, and mechanical stress while ensuring they remain securely bonded to the surrounding materials. Tempered glass. The front layer of a solar panel is tempered glass, chosen for its durability and transparency. It shields the cells from environmental factors like hail, wind, and debris, while allowing maximum sunlight penetration. Aluminum frame. The aluminum frame provides structural stability, ensuring that the panel can withstand external forces. It also facilitates easy mounting on rooftops or ground installations. Backsheet made of polymers like polyvinyl fluoride (PVF) or polyethylene terephthalate (PET). The backsheet serves as a protective barrier for the rear side of the panel. It prevents moisture and dirt from reaching the cells. Conductive materials. Thin lines of conductive metals, typically silver or copper, are applied to the surface of the solar cells. These materials transport the electricity generated by the cells to the panel's junction box and ultimately to the inverter. Anti-reflective coating. Anti-reflective coating is applied to the surface of the solar cells to reduce sunlight reflection, allowing more light to be absorbed and increasing the panel's efficiency. Manufacturing process of solar panels. The production of solar panels involves multiple stages, from raw material refinement to final assembly. Below is a step-by-step explanation of the process. Silicon refinement. Derived from quartz sand, undergoes a purification process to remove impurities. The raw silicon is heated to extreme temperatures in a furnace to create metallurgical-grade silicon. This silicon is then further refined using chemical processes, resulting in polysilicon suitable for solar cells. Ingot formation. The purified silicon is melted and shaped into cylindrical ingots using the Tucholsky process or cast into square molds. For monocrystalline silicon, single crystal seed is used to ensure uniformity. Polycrystalline silicon, on the other hand, forms a grainy structure. Wafer production. The silicon ingots are sliced into thin wafers using diamond wire saws. These wafers, typically 150-200 micrometers thick, are polished and treated to remove any damage caused during slicing. Doping and coating to make the silicon wafers conductive. A process called doping is applied. Phosphorus is added to one side to create a negative charge layer, while boron is added to the other side to create a positive charge layer. An anti-reflective coating is then applied to the wafers to enhance light absorption. Cell assembly. Doped and coated wafers are arranged into solar cells. Conductive metal lines are printed onto the cells using screen printing or similar techniques. These lines form the grid pattern seen on most panels. Encapsulation. The solar cells are placed between two layers of EVA encapsulant material. This assembly is then sandwiched between the tempered glass on the front and the backsheet on the rear. Lamination. The entire stack is heated and pressed in a lamination machine. This process melts the EVA, bonding the layers together and creating a weatherproof seal. Frame installation. An aluminum frame is attached to the edges of the laminated panel. The frame not only provides structural integrity, but also makes installation easier. Junction box attachment. A junction box is attached to the back of the panel, connecting the solar cells to external wiring. This component allows the electricity generated by the cells to flow to the inverter or battery. Testing and quality control. The solar panel undergoes rigorous testing to ensure it meets performance and durability standards. Electrical output, mechanical stability, and environmental resistance are evaluated during this stage. Innovations in solar panel materials and manufacturing. Solar industry is constantly evolving, with research focusing on new materials and production techniques to improve efficiency and reduce costs. Below are some notable advancements. Perovskite solar cells. Perovskite materials offer high efficiency at a lower cost compared to traditional silicon. Their ability to absorb a wide spectrum of sunlight makes them a promising alternative. Bifacial panels. These panels capture sunlight on both sides, increasing overall energy output. They are particularly effective in reflective environments, like snow-covered or sandy areas. Thin film technology. As materials like cadmium telluride CD and copper indium gallium selenide SiGs are used in thin film panels, which are lightweight and flexible. These panels are ideal for portable applications and unconventional installations. Recycling and sustainability efforts are being made to recycle old solar panels and recover valuable materials like silicon and silver. This reduces environmental impact and supports the circular economy.